Hi, everybody. I'm going to do a little bit of talking about a question that's been coming up quite a bit lately in terms of where should we be stopping in all these carbonyl reactions, because we've kind of seen different pathways that we can go depending on the reaction conditions, depending on what kind of nucleophiles we have, even depending on what type of carbonyl we're using. So we're going to talk a little bit about that. A lot of it comes down to equilibrium, which I'll be discussing a little bit more in this video so that we can kind of get that all figured out and straight. So I want to start with where we first started talking about carbonyl reactions using strong nucleophiles. So that's things like our, lithium aluminum hydride, organolithium reagents, Grignard reagents, and sodium borohydride. So those are our strong nucleophiles. In that circumstance, it's a lot more cut and dry because we don't have a reversible reaction. It is fully irreversible because these hydride or carbon nucleophiles are so high in energy that anything besides them is going to be lower in energy. So that's why we see the carbonyls generally are going to react to end up getting to the alcohol after the aqueous workup. We do see a change in oxidation state. So where if we start with something like an ester, once we react that, we're going to react it. So we're going to lose one bond to oxygen here. We lose another bond to oxygen there. So we end up making two new bonds to carbons, and we now have only one bond to an oxygen. So we're in a very different oxidation state than we were before. Same thing with the hydride reagents, then we're actually changing out CO bonds for CH bonds, so it's definitely a reduction. And until we end up adding our aqueous workup, it is going to be a charged product that we're getting out. So in all cases, we're ending up with our charged intermediate, which is going to be essentially the stable product until the workup step actually occurs. So because an O minus is going to be so much lower in energy than something like a C minus or an H minus, which is what we have in the starting material spot, we have a very big preference for the products to be formed because we don't want to stick around here. We want to be over here, which is more stable. So that's really kind of what we're looking at with the strong nucleophile section. I think a lot of us are feeling pretty comfortable with that because it is fairly intuitive. You've got high energy reactants, lower energy products. That's where we want to be going. So when you've got a strong nucleophile, you're generally going to be reacting your carbonyl up until it cannot be a carbonyl anymore. Probably one of the big exceptions to that is if we have a carboxylate anion with an organolithium reagent, for instance, right? We know that the organolithium is strong enough still to attack that carboxylate anion. And so we end up at this intermediate with the two O minuses. We don't have any leaving groups here. So when we do this, that's pretty much the set point of our product. And then when we add in our acid, that's when we're going to end up going to first the diol. And then we've seen how, the acetals, when they're hydrolyzed, they're going to end up going to the ketone. And by the time you form that ketone, you're already going to have destroyed your organolithium from a protonation as well. So that's kind of the one exception to that. But generally, we're going to keep on reacting those until there is no carbonyl left. So then things changed a little bit when we got to weak nucleophiles. So then we started to see a lot of reversible steps. So these are pretty much all reversible. So that's when we pulled out our equilibrium arrows, because the equilibrium process is what makes this all possible. So when you've got an alcohol, you're going to make an acetal. When you've got a primary amine, you're going to make an imine. Secondary amine is going to make an enamine. Okay. And we're just going to be talking about ketones and aldehydes for this section. So make sure that we're focusing in on ketones and aldehydes specifically, because as we've seen, when we start talking about carboxylic acids with these weak nucleophiles, it's a totally different ballgame. But let's just look at the ketones and aldehydes first. So one thing that we want to keep in mind, so our reversible products, our reversible reactions, we're going to be making neutral products on both sides of our equilibrium arrows, okay? So in the case of this reaction, if I'm making an acetal, one thing that I want you guys to think about and keep in mind is this reaction is really what we're after here. So we're looking for carbonyl on the starting material side, acetal on the other side. And keep in mind, you could just draw this the opposite way, which would just be the hydrolysis direction if you're reading left to right. But really, we should be keeping in mind these arrows and realizing that either one of these could be starting material or product. You can just flip them as much as you want, and that's really the case here. So when we do, I've already kind of drawn out this mechanism, but if you look at what's going on here, we've talked a lot about how carbonyls are really strong bonds and they're really low energy products to be making. So when you can retain a carbonyl, that's generally the best way to go. But it isn't also important to realize that we're not going to be retaining a charged carbonyl. So, and you'll see when we talk about the imines and enamines, why I say that. So, because we're not going to stop with something like this. So that's a really, really good electrophile right now. So having that methanol come in and attack is going to be beneficial, okay? And then once we get to this, which is our hemiacetal, so that hemiacetal, we really don't have anything at this point to pull that equilibrium in the direction of the hemiacetal and stop there. There's nothing that we can do to kind of force it to stop at hemiacetal. That's why they're really hard to make, except kind of in biological systems where you've got cyclic structures that end up forming. But generally, hemiacetal is pretty hard to kind of stop at because you don't have an equilibrium pull one way or the other. So that's why we see ourselves getting to this next carbonyl intermediate. But again, it's charged and there's nothing that we can do about it. So you have to have another nucleophile come in to relieve that oxygen of the charge to end up getting eventually to a neutral product, okay? So it's really important to keep in mind that each of these steps can go back and forth. It's all reversible here. So the way that we get the acetal to form is we need to remove this water. Okay, so if we look at this step, that's the step where we actually lose the water. Once we get here and we're kind of like taking away the water, really the only nucleophile that's left for us is the methanol, right? So that's the only thing that can help us deal with this positive charge here, because this is a really, really reactive intermediate. And if our water is getting removed, the methanol is the only nucleophile left. To deal with that positively charged carbonyl, okay? So it's really kind of taking advantage of Le Chatelier's principle here, where we take this away, this is still really reactive, and we're gonna start to go towards that final acetal product, okay? If you wanna go the other direction and you're starting here and you wanna hydrolyze it, then all you need to do is add a whole bunch of water, and then it's gonna try to shift the equilibrium that direction to get it back to the carbonyl. okay? So if we then compare it to the imine case, so let's look at the imine case. Again, we see a very, very similar mechanism here. So we got very similar kind of proton transfer steps, nucleophile addition steps, and all that. The really big difference, though, is that if we look at this step here, we actually have a scenario where we can just deprotonate that nitrogen and still retain a double bond, okay? So in this case, we don't need to have another nucleophile come and attack to get us to a neutral product. And I want you all to be really thinking about the fact that we are aiming for neutral products in these reversible reactions. So once we get to here, we're not gonna have another amine come and attack. We're not gonna have another amine come and attack here. So we don't see like acetal formation with nitrogen when we're adding amines, because we can still retain that double bond because we can just deprotonate that nitrogen. Okay, up here where we have the oxygen, we don't have an H on that oxygen, right? We don't have any way to really deprotonate it. About the only thing that you could think about doing is like, if you deprotonate over here, like we've seen in the enamine cases, that would just give us an enol ether. But an enol ether, we also talked about the enols, how their equilibrium tends to favor the carbonyls, right? We still want to be at carbonyl stage. And the other thing I want us to think about here is that we are not changing our oxidation state at all. So if I've got 2 bonds to oxygen here, I should end up with 2 bonds to oxygen there. Same thing over here, 2 bonds to oxygen is going to turn into 2 bonds to nitrogen. So we're not changing the oxidation state. So just kind of keep that in mind when we are working with the weak nucleophiles. That's going to be the case for all of them. But the nitrogen having 3 bonds is very different than the oxygen having 2 bonds, where generally we have a hydrogen there that we can deprotonate and still retain our pi bond here, which is preferable if we can. If we can do that, we will do that. And then we have all the same kind of equilibrium characteristics where if we remove water, we can force that equilibrium to products, okay, to our imine. So removing that water, it helps us so that we can push the equilibrium towards the imine side. Adding water means we're going to push the equilibrium towards our starting material side and the carbonyl plus amine. Okay, so that's what we see with ketones and aldehydes. If we go on to our carboxylic acid derivatives, we see something different happen again. So one thing that we want to keep in mind, this is a really important point here. A carboxylic acid with a weak nucleophile is always going to make another carboxylic acid derivative, okay? So again, we're not seeing a change in oxidation state. So in this case, we should be seeing 3 bonds to electronegative atoms. So whether that's, carboxylic acid, ester, amide, acid chloride, all those have 3 bonds to carbon with an electronegative atom. We should all end with 3 bonds to an electronegative atom on that carbon. Okay, so the other thing we want to keep in mind is that if you're starting with an ester, you should be ending with one of the carboxylic acid derivatives. Okay, so in this case, my example, I've got an ester ending in another ester, right? So you can have esters ending in carboxylic acids, or amides ending in carboxylic acids, or acid chlorides ending in amides, but they're all going to a different carboxylic acid derivative. Okay, not changing the oxidation state. So the really big important part of why that's the case is that we have a leaving group present. So all the carboxylic acid derivatives have a built-in leaving group because they already have some sort of bond to an electronegative atom, which can act as your leaving group. Okay, carbons and hydrogens, terrible leaving groups. Oxygen, nitrogen, chlorine, those are starting to be more reasonable leaving groups. So that allows us to regenerate that carbonyl and still end up with a neutral product. Okay, so just like the ketones and aldehydes, we're still aiming for neutral products. If we can keep the carbonyl around, even better. Okay, so we want to be able to keep that carbonyl. So, you know, acetals, they would love to still be a carbonyl because carbonyls are really stable, but we're kind of forcing them in that direction by removing the water. In this case, we still might have to force things a little bit using equilibrium processes. And I'll talk about that in a second, but we are still going to be ending with a carbonyl of some type afterwards. Okay, so let's just look at this example. So when we've got, so this is just a transesterification. I'm starting with ethanol, ending with methanol. So depending on which direction I want to go, if I want to go as written, starting materials to products, if I add a whole bunch of ethanol, I'm going to be pushing the equilibrium this direction because now I've kind of added too much of this. So it's going to balance that out by making a lot of that. Okay. I can go the other direction where if I add a bunch of methanol, I'm going to push the equilibrium to the other side. Okay. So that's really what we're looking at in terms of one way or the other with the equilibrium here. The other thing I want you to notice is that when we are doing the mechanism here, again, we have a really electrophilic, protonated carbonyl. And once we kind of get to this, that kind of looks like an acetal, but we still need to think about the fact that we have leaving groups around, okay? So this has leaving groups present. We can still form a carbonyl, okay? And that's exactly what happens. So we still want to be kind of leading ourselves towards carbonyl formation. If we look at the acetal version, yes. So if we look up here, once we got to that hemiacetal, we did still have a leaving group leave, right? And then we ended up here. So because that's positively charged, we talked about how we have to have something else come and help deal with the fact that this is a highly electrophilic. So the issue is the only thing that we have around is more alcohol. Okay, so we're essentially going to be destroying that carbonyl in favor of getting ourselves to a neutral product. And because we're removing water, we're forcing the equilibrium that direction. In the case of the carboxylic acid derivatives, we have leaving groups here. You know, it's kind of looking like that hemiacetal-ish thing. And when we go to reform our carbonyl, now we just have an H present, right? We don't have some R group here. So we have to have another equivalent of alcohol come in. That's not the case. We can just deprotonate that and get back to a neutral product, just kind of like we did with the imines, right? The imines keep that pi bond if possible. These are going to do the same thing. It's going to keep the pi bond. Okay, those carbon-oxygen double bonds are really, really good. So when it can, it's going to keep making them. And a lot of you have been kind of wondering about, well, what if I have this and then I have another thing of ethanol come in to do this kind of process? Okay, so if I get here and then I can just do a little proton transfer. Okay, so if I end here, or maybe even let's just make it very similar to the acetal formation stuff that we did. Let's protonate that and turn it into a leaving group. Okay, and then if we were going to do this just like an acetal, we would kick this off. Okay, and then I'd end up here. Then I would need to have another one come in to get my neutral product. Okay, final deprotonation step. And I would end up getting here. So this is actually a real functional group. This is called an orthoester. They are very, very hard to keep around. Okay, they are so heavily weighted towards this side of the equilibrium where the ester is. So this, think about it like just being deprotonated, just like a regular ester. I would say if we change these arrows to be more realistic, all of it is heavily favoring the starting materials. Okay, so the orthoester is not favored in these conditions. Okay, and it's not something that we're going to talk about in this class. They're kind of more advanced. And most of the time when you make orthoesters, you don't even start with an ester. So it's actually really, really hard to get them here. So once you're at this, that's where it really wants to stop, because it's saying, well, you know, I have a lot of ethanol around, so I can make this ethyl ester. That's enough for me. I don't need to do any more. And I can still keep my carbonyl intact and everything is hunky-dory. This is not going to happen. Okay, so let's just get a red highlighter out here. Okay, we don't want this. Okay, it is not favorable by the equilibrium. It would much rather keep the oxygen carbon double bond there. Okay, so we'd rather keep that carbon oxygen double bond than try to get rid of it in some kind of acetal situation. So just to kind of recap, this is our really important point. We're always going to be going to another carboxylic acid derivative. So make sure that you identify your carboxylic acid derivative, think about where it's going to go, and then it's usually easiest to figure out those two things first, and then go ahead and try drawing out your mechanism. It's tough on these ones to kind of let the mechanism guide you if you're still not feeling comfortable with what the product is going to be. So I would recommend figure out what the product is, then draw the mechanism for it. You can end up getting lost in all the proton transfers and stuff if you don't know kind of where you're headed, what path you're going down. before you get started. So hopefully this was helpful. I think it was a little bit longer than I intended, but equilibrium is kind of a tricky concept a little bit. So I want to make sure that we kind of are a little bit more comfortable with it going forwards. So as always, let me know if you have any questions, and hopefully you're all having a good spring break.